All right, so first thing is, what do you already know about heat and temperature? So what is the measure of how hot or cold something is? Temperature, right? Now, temperature, there is a scientific definition of what temperature actually is, but in everyday language, we tend to use how we feel as describing the temperature right now. Okay, so in here right now, show of hands, who's hot? Okay, who's cold? Anybody just okay? All right, so we each feel temperature a little bit differently. Some things, like outside, I feel like when it's freezing out, all of our guys still come in wearing shorts. And I'm like, dude, it's cold. It's cold. And they're like, it's not that cold. And I'm like,
It's not that cold.
if you ask somebody from Wisconsin, like negative 20 degrees, not so cold. Not that cold, right? So how we perceive and feel temperature is also, we got to keep that a little bit separate, because some of us might have said yesterday was really, really hot, whereas like 72 degrees is pretty comfortable, right? It was really nice. All right, so in terms of the scientific definition though, so we would say, oh, it feels hot, it feels cold. But remember we said, does cold actually exist? No, it's the absence of heat. Good. Okay, so the scientific definition is that temperature is the measure of the average, yes, average kinetic energy of the particles in an object. So the faster the particles move, we have a higher temperature. What do we use to measure that temperature with? The thermometer. So the thermometer is actually measuring the movement of our particles. We use 3 different scales. Number 1 is what we use here in the United States, where water freezes at 32 and boils at 212. What scale is that? Fahrenheit, good. The second scale, this is what pretty much the rest of the world uses. They said that water freezes at 0 and boils at 100, and then they divided all the individual parts between that by 100, and they said that that is called degrees Celsius. Good. Number 3, the Kelvin scale. Kelvin has no negative values. Okay? So think about this. So at the beginning we said temperature is how fast the particles are moving. Well, how can it be negative 20 degrees Fahrenheit? Is it moving slower than stopped? Like, how do you actually get a negative value? You see what I mean? That is where our Fahrenheit and Celsius scale aren't necessarily ideal, because how can it be negative, right? If you think about it, how is it negative, right? Because the particles can't go any slower than stopped. So with the Kelvin scale, though, we use this mostly in science, and it has the lowest possible temperature, and that is called absolute 0. So absolute 0, the slowest a particle can move is stopped. So at 0 on the Kelvin scale, 0 is actually a 0. Okay? All right, second part, transfer of energy. Hopefully some of these words you knew as well. When holding a piece of ice in your hand, the ice will start to melt. That's because energy gets transferred from what to what? Hand to the ice, right? Now your hand loses energy, right? So that's why your hand feels cold. It doesn't feel cold because the ice cube is transferring coldness to you, right? You're only able to transfer actual heat. So in general, energy gets transferred from warmer objects or objects with higher energy to our cooler objects or ones with lower thermal energy. The energy transferred between the 2 objects at different temperatures is last sentence. The energy transferred between 2 objects at different temperatures, that is heat. That's what heat is. A lot of times, the thing you got to be careful with, heat and temperature are not the same thing. Heat is the transferring of thermal energy, right? So if energy is being transferred because I have objects at 2 different temperatures, that is heat. All right, a fire can transfer energy in 3 different ways. When toasting a marshmallow, the wire holding the marshmallow transfers energy as heat along the wire and into your hand. That type of energy transfer occurs because objects in direct contact. You guys know which one that one was? Conduction. Good. I always remember it with the letter D, direct contact conduction. Okay. All right, number 2, as you stand close to the campfire, though, you feel its warmth. This warmth can be felt because of the 2 remaining types of energy transfer. Energy gets transferred through fluids like air and water by, yes, convection. Air close to the fire gets warmer, causing the density to decrease, causing the air to rise. As it moves away from the fire, though, the air gets cooler, causing the density to increase, and then it sinks, it falls. This cycle of fluid rising and falling due to temperature variations is called a convection current. Convection current. Number 3, the energy is also transferred as heat from the fire in the form of, almost, Lucy, I think you had it. You did, I heard you say it earlier. Oh, are you sure? Electromagnetic waves, or EM waves, which includes infrared radiation, visible light, and UV rays. This type of energy transferred is called, here's your word now, radiation. This type of energy transferred is the only kind that can happen without matter being present, such as in a vacuum or outer space. Okay? So hang on to that. Those are some of the words we are going to be utilizing throughout this unit. So you want to make sure you keep that, put it in your notability so you have it to access it. Okay? Let's see. Can I see it okay? Perfect. All right, so we said temperature and heat are not the exact same thing. Okay? Temperature is a measure of our average kinetic energy. How fast are those particles moving? Well, think about it. If you run really, really fast, you get pretty hot, right? If you run slow or you walk, you're not going to heat up as quickly. So for objects, as they are moving, the particles within them are in constant motion. Even if it's a solid, the atoms, if we look at the atomic level, are still moving, okay? So we have 3 different states of matter that we primarily focus on. Yes, there is a 4th, or plasma, but we talk about solids, liquids, and gases, right? Which one are the particles moving the fastest then? The gas, right? The gas is going to be moving the fastest. Ones that are solids, we said, are just vibrating in place. If we think all the way back to when we first talked about types of matter, we said that solids, the particles are really close together, but they're just vibrating back and forth. Whereas our fluids are free-flowing, and then our gases are moving really, really quickly and filling the entire volume, okay? So if I want my temperature to increase, I need to speed up the particles. And if I want to speed up the particles, then I have to put some energy in, right? I need to transfer some energy to start speeding them up. Or they have to gain energy from some source. So that thermometer, again, we can utilize. Hopefully you guys have a thermometer at home and still check your temperatures. So your thermometer is just a tool that allows for us to test how fast or how slow, bless you, those particles are moving. So if you think of like an old-fashioned thermometer, the ones with the red liquid in it, you guys know what I'm talking about? This little glass one, there's red liquid in there. So when you put that under your arm, you're heating that liquid up. When you heat it up, it's going to expand, and it's going to expand at a certain rate. And then that's where we actually read a higher temperature on the actual thermometer. Whereas now, a lot of them are way fancier and use like infrared, and they actually test that way. They use lasers to check your temperature rather than using like old-fashioned mercury. or anything like that. So it's kind of cool. So liquids, as you increase the temperature, particles move faster, going to expand. As your temperature is colder, it contracts and it decreases, and that's where you read the lower temperatures. All right, so heat versus temperature. Remember we said they are not the same thing. So temperature is just how fast are the particles moving. If they're moving fast, I record a high temperature. If they're moving slow, I'm recording a low temperature. Whereas heat is going to actually occur because two objects or two types of materials are going to have a transferring of energy. So if you take your right hand and you put it on the desk, especially the black desks. So go ahead and put your hand on the desk. So those who have a black desk, what does the desk feel like to you?
Nice and cool.
Yeah, it feels cool.
No, it feels the absence.
Okay. Now, question though, isn't that table in the same classroom as everything else?
Yes.
Yeah.
Okay, now feel the wood on the side. Is the wood as cold?
No.
Huh, that's weird. They're in the same classroom though. Shouldn't they be the same temperature?
No. I mean, we're all in the same classroom. We could be different temperatures.
But I have a temperature controlled room over there with a little thermostat that I can set this room. So all the objects in said room should be the same, right?
No.
So when you touch an object that is cold to the touch, so like when you touch the desk, it feels cold because your hand is warmer than the desk, okay? Now your hand is going to transfer some of that heat to the desk. Once you take your hand away from the desk, you're going to be like, oh man, my hand's kind of cold now, okay? And it's not that it's actually cold, it's just some of the energy got transferred to the desk, okay? If we use like infrared, we would actually see that, okay? Which would be really, really cool if we had those cool goggles. It would be sweet, okay? So as we're looking between heat and temperature, heat is a type of thermal energy. So what units are energy again? Joules, whereas temperature is just a measure of kinetic energy. And so that's how fast the particles are moving. And we measure that in Celsius, Fahrenheit, and Kelvin. Okay? So if we look at Celsius versus Fahrenheit, if we compare the two, on the Fahrenheit scale, water boils at 212. On the Celsius, it boils at 100. Okay? So there are equivalent points. There is a way that we can actually convert Celsius to Fahrenheit, if Fahrenheit back to Celsius, or to Kelvin. Okay? Most people, though, if we're going to travel to Europe, I'd love to travel to Europe right now. I'd look at the forecast and it'd say, oh, it's going to be 30 degrees Celsius. Now, traditionally in our head, we would think, oh, 30 degrees Fahrenheit, oh, that's kind of cold. Can you picture what you should pack for 30 degrees Celsius?
No. Yeah, shorts and a t-shirt. Because 30 degrees Celsius is kind of hot.
30 degrees Celsius is kind of hot. It is kind of hot. It is kind of hot. Yeah, you're right. If you take a look up here, our human body runs 37 degrees Celsius, which would be our 98.6, right? So just 30 degrees Celsius would be a little bit cooler than 98.6. It'd still be pretty hot though, right? Right. So I would probably pack t-shirts, shorts, maybe tank tops, dresses, things like that. So not that you guys have to have all the equations memorized, but I would hope that one day you guys do decide you want to backpack across Europe or travel somewhere and look at the weather and say, oh, well, it's going to be this Celsius, and be able to use your tools like Safari, Google, Siri, and figure out, well, what do I need to pack, okay? Now, I'm not going to expect you to whip out a calculator and be like, I'm going to convert this right now. But I do expect that, one day you'll go on and be like, okay, well, I can figure this out. This is how I need to pack, okay? Remember, Celsius and Fahrenheit do have negative values, okay? Now remember, I had said 0, absolute 0, is on the Kelvin scale. 0 does not actually mean 0 on Celsius and Fahrenheit. In order for our particles to actually stop moving, it has to be at 0 Kelvin. Well, 0 Kelvin is equivalent to negative 273 Celsius and negative about 460 degrees Fahrenheit. So that means particles don't actually stop moving till we get it to negative 460 degrees. Okay? So when we say, oh, it's 0 degrees out, you got to be careful. Well, what kind is 0? Because 0 Fahrenheit versus 0 Celsius versus 0 Kelvin feel completely different. Okay? Not only that, Luke already mentioned this. Can we get to 0 Kelvin yet?
Technically speaking, not yet.
No. Now we know theoretically it should exist, right? Because particles, the slowest they could move would be no motion, right? But we can't get there. Why can't we get down to 0 degrees Kelvin?
We don't have something like
Oh, we would need something that would be absent, right? Is there anywhere, can you picture anywhere in this universe right now that is void of all energy?
I don't know, maybe the vacuum space, but even then.
Yeah, so deep, deep space is pretty cold. It's about 4, 5 degrees Kelvin. But where is our source of energy? Where does all of our heat come from?
The sun.
The sun, right? And there's tons of stars out there, all going through the process of fusion. Do you remember that? Okay. So they're all releasing energy. And that energy can travel through the vacuum as a form of radiation. So we can't quite get rid of all energy. Even here on Earth, if we're like, hey, we're going to go to the bottom of the ocean, if you keep going closer and closer to the center of the Earth, what's at the center of the Earth?
Big molten core.
It's our nice hot core, right? So we can actually get energy from the Earth because of that heat, the core.
So if we wanted to reach 0 Kelvin, could we find a starless solar system?
No, we don't have that. We don't have something right now that we could actually travel to. In theory, everything will continue to cool, right? In theory, won't all stars eventually die? So in theory, shouldn't there eventually one day be 0 Kelvin out there? Just not today, not for a very, very, very long time, right? So we're not quite sure. Obviously, we know theoretical, but if we were trying to get to 0 Kelvin, we can't even build anything currently in the lab to actually get to that, unfortunately. Okay? So again, just a reminder that Kelvin scale has an absolute 0, and this is where particles do actually stop. There is no real thing as negative temperatures, right? Or at least there shouldn't be. We do have energy being transferred in the form of heat, always from higher temps to colder temps. So your body, 98.5 degrees or 98.6. The desk, about 72 degrees. So that's why when you touch the desk, it feels cold. Now, there are certain materials that will feel colder than others. What on your guys' desk is going to feel really cold? The metal, right? So if you were to touch metal, the metal is going to feel even colder. And we're going to talk about why a little bit later this week, okay? But different temperatures feel a little bit different. It's like when you guys come in here and you're like, it's so cold. And it's like, it's not. It's the same temperature as everywhere else. It's just our floor is not carpet, right? Carpet is a better insulator. It keeps things warm, right? Whereas here with the tile, it makes it feel cold. All right, so again, transferring of energy from hot to cold, even though cold doesn't really exist, so hot to a little bit less hotter. We always go from warm to cold or higher to lower energy, okay? So that is heat. Remember, heat and temperature are not the same thing. You got to get that part down pat. We said heat can be transferred in 3 ways, and you guys have hopefully remember these from all the way back in, when did you guys first talk about heat? Was it 6th grade? Man, you guys did a lot in 6th grade. All right, so we had conduction, convection, and radiation. We said the D with conduction is when we are in direct contact. That's when you actually physically touch the desk, okay? We have convection, which is our convection currents. There is a source of heat, that fire. As it gets closer, it warms up, and then it loops up, comes back down. We have convection currents with wind and water. our oceans, where do they warm? Down by the equator. And then they loop back up, right? Back up towards the North Pole and South Pole. So we do have convection currents. A lot of our weather systems are driven by convection currents. So if you're ever curious about high pressure systems, low pressure systems, what direction the wind is moving, where the fronts are moving, that all comes back to a lot of the different convection patterns, okay? Radiation, again, this is where we can actually see energy being transferred through a vacuum in the form of an electromagnetic wave, okay? So conduction, direct contact, you have to be actually touching, okay? Now remember, in gases, even though right now between you and I, it doesn't seem like there's actually something between us, remember there are still air particles between us, okay? And when those gases come into contact and they bounce off to each other, they can transfer energy that way as well. Gases, though, and liquids, mainly through convection, okay? Radiation, again, electromagnetic waves. If you look at the stove here, the person's sitting there. Whenever you're like by a fire, you're always like, ah, it feels so good, right? You would never actually physically touch the fire because that would burn you, but you feel the heat radiating off, right? There's that word that we use often. We're saying radiating because it is a form of radiation. The hot air rises, cold air falls. So in the summertime, where's the coolest part of your house? The basement, right? The basement. Do you hang out in the basement a lot in the wintertime?
Yeah.
Oh, really? Dude, my basement was always so cold at my mom's house. It's cold, right?
That's also where my place is.
Yeah, but in the summertime, you would definitely hang out down there, right? Yeah, but during winter, it's just a little chilly. Just a little. Now, when we look at boiling water, if we put a pot of water on a stove or on a fire, the stove, the metal is actually in direct contact with the stove, right? The metal and the stove touching. So that would be conduction. But within the pot, the liquid isn't actually touching the stove. But down by the stove, those particles are going to warm. They become less dense and they rise. And then they get cold again, and then they fall because their density increases. And it just keeps cycling back and forth, back and forth, back and forth. We want to make sure our pots and pans, typically, if it is made out of metal, metal heats up, right? Are a lot of our handles made out of metal? They are made out of metal, but there's usually something over it, right? Like plastic or silicone or something like that. So that part actually doesn't heat up as much so you don't get burned. So we said our energy coming from the sun to the earth is through radiation, right? Because it is a vacuum, there's no particles, no direct particles for it to touch, nor particles for it to form a convection current in order to transfer the energy here. So it has to come by a different way, okay? Where we are going to stop for today. All right.